In this video, we're going to work some example problems related to the net change theorem. And so remember, the net change theorem states that if you're doing a definite integral of a function to where the function represents the change in some quantity with respect to time. Now, the independent variable doesn't have to be time to apply this theorem, but when the independent variable is time, that's the easiest way to illustrate the theorem. So again, you're taking the definite integral of a function that represents the change in some quantity with respect to time, like velocity represents the change in position with respect to time, acceleration represents the change in velocity with respect to time. So you're taking the definite integral over some interval, and it would be the interval of the independent variable, so time. Then that integral itself, the answer to that integral, the value, is equal to the net change in the quantity over that time interval, the quantity itself. So you're doing a definite integral of the change in some quantity with respect to time, so that you're doing a definite integral with a rate function. But then to evaluate the definite integral, you are seeing what is the net change in the actual quantity itself over the interval. And so the net change in the quantity itself over the interval, you're saying what is the quantity at the right endpoint of the interval and subtract that from the quantity evaluated at the left endpoint. That's it. So it doesn't matter what's going on in between, what the quantity is doing in between. You're only looking at the endpoints. Okay, so let's look at the first example. If oil leaks from a tank at a rate of R of t gallons per minute at time t, what does the definite integral of this function from 0 to 120 minutes represent? Okay, so we want to evaluate a definite integral. The definite integral is of a rate function. So it's the change in some quantity with respect to time. Now, again, the net change theorem, it's not only with respect to an independent variable, that's time. It's really any independent variable you can apply this to. But again, it's easiest to illustrate when time is the independent variable. Okay, so this is a rate function. The rate function implies time, but I still want to point out that the independent variable doesn't have to be time. But in this problem, it is. So we're taking the definite integral of this rate function. Okay, and so it's a rate function because it's some quantity per unit time. So what is the quantity? And it's helpful whenever you're stating what the quantity is, be really specific, because that's going to help you understand and answer the problem correctly. So what I'm saying is, what I mean by that, the quantity is obviously like gallons, right? But let's be even more specific. It's gallons of oil, but we could be even more specific of that. It's not because is it gallons of oil in the tank? No, it's gallons of oil that has leaked from the tank, right? Oil leaks from a tank at a rate of R of t gallons per minute. So it's the rate is the number of gallons that have leaked from the tank per unit time, per minute. So the quantity is the number of gallons that have leaked from the tank. That's the quantity. And we're doing a definite integral of the change in that quantity with respect to time, specifically from 0 to 120 minutes or 2 hours. Okay, so if we understanding the net change theorem, then what is the answer to this definite integral? What this is going to be if we had another function that represented let's say it's Q, that's the amount of oil that has leaked from the tank at time t. So at time t is equal to 0, there's no oil that's leaked. I guess they just filled up the tank. But then, every 1 minute, 2 minutes, etc., you have a certain number of gallons of oil that have leaked from the tank. That's what Q of t represents. And so in that case, this definite integral would be equal to Q of 120 minus Q of 0. Now you might say, well, isn't Q of 0 0? Probably, but it doesn't have to be. So, and it doesn't give us any information about that. So it just depends on the boundary conditions. At time t is equal to 0, maybe they're saying there's already been 3 gallons of oil that's leaked. Okay, if x is measured in meters and f of x is measured in newtons, what are the units for this definite integral? So yeah, here's a situation. So I'm not sure, they're not asking us about the net change, to use the net change theorem here, but just a reminder, you can apply the net change theorem for any independent variable. Okay, and so, okay, x is measured in meters and f of x is measured in newtons. So what's the units for this going to be? Well, okay, think about how the definite integral was developed. So even though the definite integral can be used for all kinds of applications, you can think about how the application that it was developed with the area under the curve application. Okay, so this represents the area under the curve of this function here. And so what are the units then? It's the units of the y-axis times the units of the x-axis. This here is going to be in Newton meters for sure, which is energy, it's joules. 1 Newton meter is a joule. Why? Because we're doing an infinite sum on the areas of these rectangles. So you're doing the height of the rectangle, which is in newtons, times the width of the rectangle, which is in meters. And you're just adding up an infinite number of those rectangles. So the result is Newton meters, or again, joules. The marginal cost of manufacturing X yards of a certain fabric is given by this formula here in dollars per yard. Find the increase in cost if the production level is raised from 2,000 yards to 4,000 yards. So yeah, here's a good example where the independent variable is not time, but we can still apply the net change theorem. And so this function here represents the change in some quantity with respect to an independent variable. In this case, the independent variable is yards of fabric. So let's be as specific as we can be here. So the independent variable, again, is yards of a certain fabric manufactured. So it's how many yards of this fabric have gone through and completed manufacturing. Not how many yards of fabric have you purchased for manufacturing. It's yards of fabric that have been manufactured. Okay, that's the independent variable. And then for this rate function here, the dependent variable is dollars, but you want to be specific. Dollars, so what does that mean? It's the cost to manufacture, the cost in dollars to manufacture each of those yards of fabric. Okay, so the question is asking then, find the increase in cost if the production level is raised from 2,000 yards to 4,000 yards. Okay, so the increase in cost. The cost is the quantity here, right? The cost, that's the dollars to manufacture, the dollars spent to manufacture, the cost of manufacturing. Okay, so that's the quantity in this rate function. And we know from the net change theorem that if you do a definite integral of a rate function over an interval, then the result of that is of that definite integral is the net change in that quantity over the interval. And so the increase in cost, like, all right, the cost is going to be just C of X, right? This is the cost to manufacture X number of yards of this fabric. And so what they're asking is, if we're going to go from manufacturing 2,000 yards to 4,000 yards, what's the increase in cost? What's the change in cost? And so you can see what's going on with the cost function in between 2,000 to 4,000 doesn't matter. They're strictly asking us, what is C 4,000 minus C 2,000? That's all they're asking. Okay, well, based on the net change theorem, we know that this is going to be equal to this definite integral, right? Because this is the quote-unquote rate function. It's not a rate, but they're asking for the change in some quantity over an interval of the independent variable. And we have a function that represents the change in that quantity with respect to that independent variable. So we've got the quote-unquote rate function. So all we need to do is evaluate this definite integral. Let's do that. Okay, so Okay, so we can separate this into 3 separate integrals. Okay, so now this integral here, the first integral is going to be 3x. Well, let me put an equal sign. Okay, so we've got 3x, then from 4,000 to 2,000. Okay. This is going to be, so that's 1 over 100 out front, that's 0.01. So what we'll want to do is we'll put, it'll be 2x squared. No. Nope. It'll be, this will be a 2. X squared. So you bring down the 2, this goes to 1 over 100. You're left with 1 over 100x. So it's 1 over 200, and then from, okay, but 1 over 200 x squared. Okay. Okay, now this would be, so what is 0.000006, and we want to divide that by 3. That would be 0.2x cubed. Right, because you bring down the 3, you get 0.000006 x squared. Okay, then from 4,000 to 2,000. Okay, so we can factor out the constant, and we've got 4,000 minus 2,000. Okay, and let me just make this 0.02. Okay, now 4,000, well, 4,000 squared minus 2,000 squared. Okay, and then 0.1, 2, 3, 4, 5, 2, and then 4,000 cubed minus 2,000 cubed. Okay, so let's see. So 4,000 squared minus 2,000 squared is 12 million. Okay. Now 4,000 cubed minus 2,000 cubed is, that's 56 with 9 zeros. Okay, so this is 4,000 minus 2,000 is 2,000. 2,000 times 3 is 6,000. Minus 0.02 times 12 million. That's 240,000. Plus, and then 56 million times, then it's 0.123452. 112,000. Okay, so I'm messing something up here. 4,000 squared minus 2,000 squared. Okay, so 1 divided by 200 is 0.005. That's where I messed up. Okay. All right. So with that, we've got, so we can take this 12 million, then that's times 0.005. That's 60,000. Okay. So now we've got 6,000 minus 60,000. It's 58,000. So there you go. The increase in cost is $58,000, and we didn't have to find get the full cost function. We did do the antiderivative, but we just had to just do it straight from the definite integral, and we got this value. So the increase in cost, the cost function, if you take the cost function evaluated at 4,000 yards and subtract that from the cost function evaluated at 2,000 yards, that's 58. It would be $58,000. Water flows into and out of a storage tank. A graph of the rate of change, R of T, of the volume of water in the tank in liters per day is shown. If the amount of water in the tank at time t is equal to 0 is 25,000 liters, use the midpoint rule to estimate the amount of water in the tank 4 days later. All right, so water flows into and out of a storage tank. A graph of we have a rate function here, and what is the units of the rate function? And be very specific. It's the rate of change of the volume of water in the tank. So not leaking out of the tank, not coming into or out of the tank. The volume of water in the tank. So it's the quantity here is the amount of water in the tank at some point in time. That's the quantity. This function here is representing the change in that quantity with respect to time. This is a rate function. All right. If the amount of water in the tank at time t is equal to 0 is 25,000 liters, then use the midpoint rule to estimate the amount of water in the tank 4 days later. And so here's day 0, and then here's day 4. And so we know that the definite integral of a rate function over an interval, it represents the net change in the quantity associated with that rate function. And so we know that the definite integral of this rate function from 0 to 4 would be the net area under this curve from 0 to 4. And so that net area is going to represent the net change in the amount of the volume of water in the tank from day 0 to day 4. Okay, so if that would be, we'll call that V of T. That's not what this function is. That's the actual volume of water in the tank at any point in time. And so but the net area under this curve, which would be going from 0 to 4, and this is R of T, we know it would be V of 4 minus V of 0. Okay? So we can, what it wants us to do is use the midpoint rule to get an estimate for this area, because it doesn't give us this function, but we can use the midpoint rule to estimate this. The net area under this curve, which is an estimate for what this is. And so we can get an estimate for this. But once we have this, what it's asking us is it wants to know what V of 4 is. But what is V of 0? Well, it gives us V of 0. V of 0 is 25,000. So once we get the estimate for this area, the net area under the curve, then we can find V of 4. So, okay. What we're going to do is we're going to, this here is approximately equal to what? Because we're not going to get the actual definite integral. We're going to get an estimate. We're going to do this using the midpoint rule. Okay? And so we can let's make each tick mark an interval. So we're going to separate it up into, there's one interval, there's another, okay, like that. All right. Now, with the midpoint rule, what that means is that the height of each block, so this is the width of each block. It doesn't, I don't think it tells us what width we're supposed to choose. So yeah, I mean, it's probably, they probably just, they want you to use each tick mark. So this is the width of each block, but you have to choose, when you're doing an approximation, you have to choose what the height is going to be. Well, it's telling us to use the midpoint rule. That means that the height of each rectangle is going to be the function evaluated at the midpoint of the rectangle. So here it would be, there's that rectangle. Okay, here it would be, so this, not the left endpoint, not the right endpoint, right in the middle there. See? Here would be right at that peak point. Okay, here it's like right there. Here it's like right here. Here it's like, okay, and then but we're going to subtract the areas of these rectangles. Okay, and then right there. Okay, so the delta x is going to be 1/2. We can just factor out the delta x and then just add up the heights. So, okay, each is 500. So 500, 1,000, 1,500. This is 1,250. This is about 1,750. This is about 1,850. This is about, looks like 1,750 as well. This is about 1,100, maybe 1,075. Okay, this is about 250 or 275. Okay, now subtract. This is about minus 400. Okay, and then this is minus 1,000. So got 1,250 plus 1,750 plus 1,850 plus 1,750 plus 1,075 plus 275 minus 400 minus 1,000 divided by 2. So 3,275. Okay, so now we want to find V of 4. And so V of 4 is equal to what? It's plus V of 0. So 3,275 plus 25,000. $28,275. So V of 4 is approximately, because this is an approximation, equal to 28,275 liters. All right, shown is the power consumption in the province of Ontario, Canada for December 9th, 2004. P is measured in megawatts, T is measured in hours starting at midnight. Okay, using the fact that power is the rate of change of energy, estimate the energy used on that day. So it's the power usage. So we're at midnight on December 9th, 2004. The day has just started, and then each tick mark is like a certain number of hours past midnight, and that this represents the power consumption in Ontario, Canada. So, you know, this is kind of confusing because you would think, well, wouldn't the power consumption always go up? Well, yeah, the energy, the total energy used would always be going up. I mean, it's never, so the power consumption is never negative. That wouldn't make any sense. Because like all that, then you would be like, there would be like the city is, the people in the city are giving power back, giving energy back to the power plant. That doesn't make any sense. So it's never negative, but it's just saying like this would be at 3 a.m. There's more power consumption at midnight than there is at 3 a.m. And then when actual morning, the day is starting, 7 a.m., 8 a.m., then the power consumption there's more power being used. That's the idea. And they're saying, estimate the total energy used on this day. So if we had a function for the total energy used as a function of t, that would always be going up. That would be an increasing function. It would be increasing for the whole time because, again, at every moment in time, there's at least some power being used. Like the power is energy per time. Power is a rate function. It represents the change in energy per time. The change in energy per time being used by the city is always positive. So as time increases, the amount of energy used by the city is increasing. But we know if we want to get so we're not trying to find the actual formula for the energy used at a moment in time. We're trying to find the net change in energy used from time t is equal to 0 to the end of the day. And we know we don't have to find out what is E of 0. E of 0 is going to be 0 because the day just started. The question is asking what is the amount of energy used on this day. So we know E of 0 is 0 because the day just started. And we're trying to find E of 24. So how do we do that? Well, we know that if we have, so the power function, if we can integrate the rate function, which is the power function, from 0 to 24, do a definite integral, this is going to be equal to E of 24 minus E of 0. But we know this is 0. So if this is going to be equal to E of 24, okay? So, but what is this? This is the area under the power curve, right? Well, we have the power curve here. So if we can just get an estimate for the area under this curve, that's going to be equal to E of 24. All right? So, if you were doing this in real life and all you had was the power curve and you couldn't get a function for this, well, you could take your time and do this kind of accurately, right? But, we've already done a bunch of examples on doing, finding estimates for areas under curves. So I'm not going to go through this very slowly. Like, you get the idea. If you wanted to do this slowly, you could do the midpoint rule. You could do whatever you want. But so, all right, each tick mark here, let's get an estimate for this. Each tick mark is 16, 17, 18, 19, so 1,000 units of power. All right, so this would be, all right, the first block is, okay, well, each interval is 1/3. Okay, so E of 24 is approximately 1/3 times, okay, what is this height? That would be 17,500. What is this height? If we think about the midpoint, so, all right, this would be 17,000, so 16,800. I mean, whatever. I'm not doing this that carefully. This would be about 16,600. Then this would be 16,500. Then this would be 16,700. Okay, so now we're here. This would be 17,500. Okay. This would be about 18,500. Okay, this would be about 20,800. Okay, here it's about 20,500. 20,600, and then 21,000. Okay, and then about 21,100. Here, 20,800, and then 20,500. Okay, here it's 20,300 and then 20,600. Okay, about 20,950. Okay, here we've got 22,000 and then 22,300. Okay, 21,900, then about 20,500. Okay, now here that's 20,500 and then 19,500. Okay, now here 18,500. Okay. All right, so let's add this up. Okay, divided by 3. 158,150. Okay, so this is in, these are megawatts, so, megawatt hours. This is 158,150 megawatt hours is the amount of energy used in this day.